Okay.
Ruben, so let us know when we should start.
Yeah, I think probably another minute or so, then we
Okay.
should totally start it.
Okay.
Okay, so
Ruben, so let us know when we should start.
yeah, I think probably another minute or so, then we should totally start it. Oh, sorry. Okay, maybe let's start now. Yeah, I think it's 32 on my desk.
Okay, so then let me start with a little introduction, right?
Yes.
Okay, hello everyone, and welcome to the first webinar on quantum chromodynamics organized by the Coordinated Theoretical Experimental Project on QCD, or CTEC. Now, I would like to start by thanking our host, Professor Huiwen Lin from Michigan State University, for taking an initiative of organizing this webinar. Hopefully this will become a regular series of webinars dedicated to various aspects of hadronic physics. I would like to start by first introducing CTEC a little bit to the people who are not very well familiar with it. So I'm co-spokesperson of CTEC. So CTEC is a collaboration of theorists and experimentalists working on various aspects of hadronic physics. CTEC, was formed in 1990 and originally consisted of about 20 experts working on hadronic physics. So the main focus of CTEC is to bring together experts or scientists working on various domains of hadronic physics. So we know that QCD is a very rich subject, and it is also a very complex subject. So the phenomena that we study in QCD are very fascinating and have many important technical details. And it is important for members of various parts of a large community working on QCD to talk to one another. So one of the essential tasks of CTEC is to facilitate conversation among various parts of the QCD community. And as I mentioned, this involves helping theorists talk to experimentalists and back, helping scientists working on high energy aspects of QCD to talk to non-perturbative QCD experts. And of course, as QCD has been evolving, the focus of research covered by CTEC has been also evolving. Now, in particular, right now, CTEC is quite closely involved in planning of the electron-ion collider, which is a major experiment in the United States that will bring together QCD experts working both on the low energy and high energy physics, and we see multiple areas for fruitful collaboration between communities as we plan the future EIC experiments. Huiwen, our host today, is an expert on lattice QCD, and we also look forward for important contributions from lattice QCD in the coming years. And now, finally, of course, we have a very large experiment, the Large Hadron Collider, but also small experiments working on QCD are still very important. And so today's webinar will demonstrate clearly that it doesn't matter what the size of the experiment is. We can learn a lot from experiments at relatively small energies, but cleverly designed. So our speaker today is the CTEC member, Professor Paul Reimer from Argonne National Laboratory, and we will discuss an important measurement which was published last month in Nature, dedicated to the asymmetry in the antimatter of the proton. So now Huiwen will be hosting this meeting, and I don't know, perhaps, well, my understanding is that this meeting is being recorded, but also, well, you can submit your questions and comments in the chat, and Huiwen will host the Q&A session after this talk. And so with this, I welcome Paul to begin the presentation.
Okay, thank you. So one thing I wanted to say in terms of questions and answers, while I don't think I can see your hands raised, please feel free to raise them, and Hue can interrupt me during the talk, because in this format, it's very hard to get audience feedback. So I appreciate any audience feedback I can get. So I'm talking about the SEAQUEST'S today. And so this picture on the right are my two children about 5 years ago going out to explore the sea, Lake Michigan as it happens to be. But so I'm going to sort of put a nautical theme and some sea pictures in this to help it go along. That's interesting. Okay, doesn't want to go to the next one. There we go. Okay, so starting out at the most basic level, we were all taught that the proton is made up of these three quarks, two up quarks and a down quark, and they had this color charge thing that held them together, and we were quite happy. But in reality, things are much different. They're held together by the color charge. The color charge, as you know, is carried by the gluons, and the gluons interact with them and self-interact. And so through this process, those gluons have enough energy in their field to spontaneously create quark anti-quark pairs of color anti-color. And so eventually, the proton that you're thinking of as those three valence quarks looks like this, with a whole bunch of gluons that I didn't bother to draw. And then one has to ask the question what valence means. And in a lot of drawings of the proton, you still see three large quarks with all these little C quarks around them, but that's not true. The valence only means that there's an excess of two U quarks over the anti-U quarks, and one D quark over the anti-D quarks in the proton. And if you think about it, it's pretty amazing that with this large number of quarks in the proton, that those three quarks, a difference of between two U quarks and one U quark, dictate most of the properties of the proton we can see at low energy. So now I'm going to be talking about them at high energy, or higher energy, where we can see things. And so the quarks, you know, we refer to them as partons. And so I went back to look at what the parton model, you know, where did it originate? And so I was able to see that almost all references to the parton model go back to this one Fizerev letter by Richard Feynman. And it's a very interesting Fizerev letter. It's like 2.5 pages long. It only contains 2 footnotes. One of them defines some technical terms, and the other one gives a reference to something he might eventually write. But if you read the paper, the key thing is highlighted here, that his paper is not deductive reasoning, but it's inductive reasoning. And he gives sort of some general arguments why he thinks that, in fact, the proton's probably made up a whole bunch of point scatterers. And then he concludes that he's given only the barest indications of the logical basis of these suggestions indicated here. And perhaps in a future publication, he'll be more detailed. So I tried to look up footnote number 2. It's to a conference proceeding that was given back when conference proceedings were not online. So, you know, it's an interesting paper, and I think only Richard Feynman could have gotten something published like this where you say, perhaps I'll expand on it in the future. And I don't have any real reasoning for this, it's just a hunch. But Richard Feynman, as we know, was very smart, and he basically said the proton looks like this, and all of the things we see now say it does. Okay, so those quarks and gluons in the proton are distributed as some function of a variable we like to call x. X is the Bjorkane x, the fraction of momentum carried by each of the parton we're looking at. And so back in the late 80s, early 90s, there sprang up several efforts to see if we can describe these distributions of partons in the proton. And one interesting thing was, it was sort of always assumed that this myriad of SEAQUEST'S that I showed you before, oops, wrong way, here, all came from gluons splitting into D anti-D and U anti-U pairs. And so if you take that view, then you should have, except for a small asymmetry due to the mass difference of D and U quarks, which is small compared to the proton, you would expect that the C gets generated through QCD evolution, but at some very low Q squared, you would have no C. It would just be those 3 valence quarks. And so under that assumption, there was an attempt to fit all the data that we had that was directly related to parton distributions to functional forms. And what they found is, in fact, highlighted in red here, a requirement of a valence-like parton structure for all parton distributions at a very low scale. So by valence-like, they mean sort of primordial, or it's always there. So you always have, even at low scales, an anti-quark distribution in the proton. And so the picture on the right here is from that paper, and you see down here a small contribution of U bar to the proton, even at low Q squared of 300 MeV. So one thing to note, however, is there's no distribution of D bar. There was still an assumption that even though it has to be there, it's all going to come from this from some symmetric process that produces U bars and D bars at the same rate. Okay, and that was a beautiful picture until the NMC experiment managed to measure the Gottfried sum rule. So the Gottfried sum rule is basically this integral of F2p minus F2n from 0 to 1, and you should get 1/3. So plotted on the right axis here is F2p minus F2n, and those are the black points, and that's what they measured. They actually measured F2 on the deuteron, and from that extracted F2 on the proton. And then if you take the integral, which is plotted in the left axis, and the blue points, this is the integral. So the furthest right point is the integral from basically 0.6 to 1, and the next one's from 0.5 to 1, and so on and so forth. And you see their integral comes up nicely. And if you do an extrapolation over however many decades in log x you want to go, you see that it comes out to a value much lower than 1/3. It comes out to 0.2 something, and 1/3 is clear up here. And so there are a couple ways you can explain that. But one of the ways, and probably the easiest way, is to just give up on the fact that D bar is equal to U bar. If you do that, then this integral does not have to equal 1/3, and you're doing well. You could also just say that something weird happens here because you can never measure to x equals 0. You could claim that this suddenly goes up. There are other arguments, but this d bar not equal to u bar is a decent explanation of this. So shortly after that experiment was done, the NA51 collaboration at CERN was in a very fortunate position where they could measure this with Drell-Yan with the Drell-Yan reaction. And I'll tell you what the Drell-Yan reaction is a little bit later. But for now, just take my word for it that you can measure anti-quark ratios with Drell-Yan. And what they measured here was at one specific value of x, 0.18, and they found that basically there were twice as many anti-D quarks there as there were anti-U quarks there. And that is really weird. So then that data was, of course, included in parton distribution fits, along with the integral from NMC. And so in the mid-90s, these two curves here, the cyan and magenta curves, show basically the status of what we thought we knew about d bar over u bar. In the late 90s, when I was a postdoc, the Fermilab NUSI experiment then used Drell-Yan, the same technique, to measure d bar over u bar over a much wider range. They had a spectrometer that could accept values of x from, sort of near 0, I can't say 0, to out around 0.25, 0.3, and then their acceptance tapered off rapidly. And what they found is the data here in blue. And the interesting thing is how that data was able to reshape the CTEC fits, or all of the fits, but here in particular I put CTEC. And you see, rather than going up like the cyan curve, you incorporate this data and it drives the fit down. My point in saying that is our knowledge of these parton distributions is really driven by data. Now, for the valence distributions or the quark distributions, there's a lot of data out there. And so the fits don't change that much from one version to another. But for the C-quarks, it's very hard to find something that selectively looks at the C-quarks. And so, well, QCD will tell us what these distributions will look like at some Q squared once we know what the distributions are somewhere. It doesn't tell us initially what the distributions are. So as I said earlier, you can get from perturbative QCD, you expect sort of a symmetric d bar equals u bar c, but there are hadronic degrees of freedom you need to consider. One of them is illustrated here, the PION cloud model from Jeremiah Sullivan at Illinois. It's a simple model, but I like it because it's intuitive. And so in this intuitive model, you imagine that the proton spends some of its time as a bare proton, and some of its time its wave function is a nucleon and a pion. And some of the time its wave function is a delta and a pion. And some of the time it's a lambda and a kaon. And you can just continue to expand this series. Of course, the contributions get smaller and smaller as the mass balance becomes more and more out of whack. But you can imagine this. And then you can actually have your undergraduates, once they've had intro to quantum mechanics, look up the Clebsch-Gordon coefficients and the spin on these things and come up with what these normalizing factors should be. And you get a picture of a non-symmetric C in the proton. The meson cloud is not the only model. There's a number of other ones listed here. One of the interesting things about these models, though, is they don't just predict something about d bar and u bar in the longitudinal parton distributions, but a lot of them also make a comment on what the net spin of either d bar or u bar or d and u is in the proton. So there's two areas then that you can test these models. Okay, so one last little thing on models that's interesting to consider. Perturbative QCD, that gluon splitting that I sort of dismissed, occurs. We know that. And so if you want to look at just the non-perturbative part, you can imagine dividing up the quark distributions into a perturbative part, and here I called it meson, but non-perturbative part, and make that for the U and the D. And to the extent that, as I argued, D bar is equal to U bar from perturbative QCD, if you look at the difference, then you get the difference in this, then you get simply the non-perturbative part. So plotted on the right here is our 866 NuSi data, along with data from Hermes that used another technique. And some of these various hadronic models that do more or less, and take that with a grain of salt. So some of these look nice, and some of them miss by several sigma, but they get the general shape right, more or less well describing D bar minus U bar. I should say that in the near future, the lattice is going to weigh in on this. And while I had argued before that we know how to evolve the shapes, we don't know what the shapes are. To start with, though, lattice, in fact, can tell us that. And so here is, again, the E866 data plotted with two predictions from the lattice. These are several years old now, but they were the first predictions to come out, and I was very happy to see them. This was I considered it a big advance in our knowledge, at least of the C parton distributions. Okay, so
question, Paul.
Yes.
Yeah. So can you please ask the question? So let me allow you to talk. Okay. So let's see. Raise hand. Okay. Was there a question? No. Okay.
Okay.
Okay. Let's continue then.
Okay. Okay. So then I'll continue. So
okay,
continue.
So maybe ask Tom. Well, let's see. Maybe you have a problem with the microphone. No. Okay. Well, let's just continue. Sorry.
Okay. Okay. So continuing with the voyage into the sea, you have to choose which boat you want to sail into the sea. And there are lots of ways that you can explore the parton distributions. And just a few of them are listed here from deep inelastic scattering, neutrino, muon measurements, and then semi-inclusive deep inelastic scattering. The thing to notice on the first three here is there is really nothing to distinguish between the quarks and the anti-quarks. And so if you just want to look at the sea, you have to have something slightly different. So you can do that with semi-inclusive deep inelastic scattering, where you detect a outgoing hadron, and if you have the fragmentation functions, you can work backwards. There are a few other ways. W production at collider can give you something proportional to the anti-quark distributions. And then there's Drell-Yan, Drell-Yan reaction, which is what I'm going to spend the rest of this talk on. So Drell-Yan was named for two people that we all know, Sidney Drell and Mungtung Yan, who hypothesized this process to explain the data set that I'm showing here. So this was a search at Brookhaven for some sort of massive particle that would decay into two leptons. And so they plot here the cross section. They say it varies smoothly and exhibits no resonant structure from low mass to high mass over many, many, many decades of cross section. So then Sidney Drell and Tungmao Yan said basically, how do we get this cross section that varies in this way? And they hypothesized that it came from the annihilation of a quark in one of the hadrons. The experiment used a proton beam and a uranium target, with an anti-quark in the other one, into the mu pair that they detected. And they predicted a cross section that looked something like this. They also predicted that should have an angular distribution of 1 plus cosquared theta. Here is some data from 866. It has a beautiful distribution like that. And so while there were other explanations for this cross section at the time, this is the one that stuck. I forgot to mention that you always have to be careful of the conclusions you draw. While they see no resonant structure here, Christensen, Hicks, Letterman, there actually was. This was the J psi. And had they recognized this shoulder here as what it happened to actually be, they would have been credited with the discovery of the charm quark. As it was, we had to wait a little while to see the discovery of the charm quark. Okay, so Drell-Yan, as I said, is an annihilation of a quark with an anti-quark. And those are supposed to be bars, but I don't know what happened. It annihilates into a virtual photon that then decays into a lepton pair. So it's basically point-like scattering of spin 1/2 particles. And you can go and look it up in your favorite high-energy physics textbook. The derivation of this cross-section, I use Halzen and Martin because that's what was in favor when I was a grad student. And you can just easily derive this cross-section. You then have to convolute it with the probability that you actually see, or that there is actually an anti-quark in the target at the particular X value, and a quark in the beam, or flipping it over, an anti-quark in the beam and a quark in the target. And so in leading order, it's a very easy cross-section to derive. If you have a fixed target spectrometer where everything is boosted really far forward, like NuC and like the SEAQUEST experiment that I'm going to talk about, you have very, very few anti-quarks in this regime. Well, you see you have acceptance for very, very few anti-quarks in this regime. So you mainly see this first term, and it turns out because the charge is squared, you mainly see U quarks in the first term. So anti-U quarks in the target, U quarks in the beam. And then if you switch to a deuterium target and invoke charge symmetry, you see the anti-D quarks in the target. And so then if you take this equation, make a few approximations, including this one, it's fairly easy to come up with this equation here that says the ratio of proton deuterium to twice proton is equal to 1/2 times 1 plus d bar over u bar. In leading order, simple equation, but a beautiful motivation for measuring these cross-section ratios. Okay, so I said leading order. Half the cross-section roughly comes from next to leading order diagrams. And so that makes it a little more difficult, but conceptually, if you look at these, a lot of these diagrams are still quark anti-quark annihilations of some form. You just end up having to integrate over the gluon, so your kinematics are a little bit different, but they're still quark anti-quark annihilations, and they still give you sensitivity to the d bar u bar ratio. There are, of course, a few, the quark gluon diagrams that then serve to dilute your sensitivity. But in general, the sensitivity to d bar over u bar, sorry about that, remains. Okay, so we chose to sail into the sea and look for d bar over u bar. And so the ship we chose was this new one that we built out of old parts called the SEAQUEST'S spectrometer. It was basically a Frankenstein conglomeration of pieces from many, many, many experiments that had happened earlier at Fermilab and at DAISY and probably at other places, along with, as we had money, some new components that we were able to add. So the beam comes in to our experiment from the left, hits some liquid hydrogen, liquid deuterium, and solid targets here. The beam that doesn't interact in the targets, 90% of it, hits this solid iron magnet and interacts and showers and is absorbed by the time you get to the end of the 5 meters of solid iron. And it's magnetized, so the particles, charged particles, curl up in circles, and they have a much longer path length than the iron, so we really do get rid of most of them. What makes it through, however, are neutrinos, which we never see, and muons, which is what this spectrometer was designed to detect. So we see muons from this interaction, the two muons going through this, and then we see them in a set of tracking chambers. We bend them in another magnet, then more tracking chambers, a wall of solid iron, again, about 1 meter thick, and then more tracking chambers. This is to make sure that if somehow a PION makes it through, we catch it here. The experiment took place at Fermilab. One difference between this experiment and the predecessor experiment that I showed you earlier was the fact that we now had a beam of 120 GeV protons coming off of Fermilab's main injector, rather than the previous experiment having a beam of 800 GeV protons coming off of the tevatron. That is an important thing that I skipped over when I was showing you the cross-section. The cross-section has this 1 over S. S is the center of mass energy squared. So as you go down in center of mass energy, you go up in cross-section. So that means you have a longer reach and can see lower statistics areas. So this was an important change. It gave us a factor of 7 in the cross-section. So we built the spectrometer, we turned it on, we got beam, and this was basically all of our expressions when the beam hit the target. The whole detector lit up. So on the left here is an event display. Red indicates a wire in the tracking chamber that was on. And while I have seen pictures from Rick and LHC where they draw tracks to things like this, we couldn't. If every element is on, it's just the same as every element being off. And so we had to figure out what to do. Well, we quickly figured out that this was coming from the fact that the beam was not coming in a uniform way. So we put the macroscopic structure of our beam was that every 4 seconds we would get a pulse of protons. Microscopically, those protons were delivered in 19 nanosecond buckets. So every 19 nanoseconds, we got basically a pulse of protons that nominally contained like 40,000 protons. But it didn't. It varied from 0 protons to many, many protons. Averaged over the entire 4 seconds was what we wanted. But instantaneously, we saw many more protons, and then no protons, then many more, then none. So all the events we saw were from when there were many more protons, and that's what was lighting up the experiment. Here's a graph of what we saw at a 10 kilohertz level, so not the 53 megahertz that this is, but at a 10 kilohertz level, phase locked to the 60 hertz AC. And so you can see that this is just ripple coming in from the power line into the accelerator facility. So this was in our commissioning run. We did something that you shouldn't do, but we wanted to see data in our commissioning run. And we used the detector as a measurement of beam luminosity and vetoed on high beam luminosity. Once we did that, you got beautiful tracks going through the detector. Here are 6 wires intersecting nicely and a hodoscope paddle intersecting nicely behind them. Here's the other muon, same thing. It was a world of difference. So this is our commissioning run. We took data like that as part of our commissioning. Here is a plot of our mass histogram. So the invariant mass of the 2 muons reconstructed in the reconstructed. The black is our data, the blue and the red are Monte Carlo. And what sticks out there is you can see the J psi. And that's a clear sign that you're doing something right. If you can reconstruct the J psi, that gives you your mass resolution. So we were happy that with the restricted luminosity and the veto we put on, we were able to see the J psi. Going forward, though, you can't veto beam intensity on what you see in the detector unless you want to induce a huge systematic in terms of rate dependence. So we put in a shrink-off counter that was capable of monitoring the beam intensity on the 53 megahertz scale time resolution of the beam, that 19 nanosecond bucket. So we built a shrink-off counter, put it in the beam, and then we were able to measure the distribution of beam intensity every 19 nanoseconds. And so here are two plots of the beam intensity. Each bin is a 19 nanosecond bucket. And this is what the beam looked like half a second apart. So at one point, basically, we have nice even distributions of low intensity beam. And half a second later, we have beam that's going all over the place. So what we did is we put a veto in at about 65,000 protons, and we basically shut off the detector for times when the beam was above 65,000 protons, and in fact, through the miracle of delay cable, for basically a window of 100 and some nanoseconds around that to give our chambers time to clear. One interesting thing is if you take these distributions and you want to see a perfect example of how to apply a Fourier transform, this is a Fourier transform of those time distributions. And what you clearly see again is that it is radio frequency from the AC power supplies leaking into the magnets in the accelerator. You see 60 hertz and the harmonics at 120, 240, 360, 720. This was, when I told one of our grad students to do this, they didn't understand why I wanted a Fourier transform plotted. They did it anyway after my insistence, and then they understood really what a Fourier transform does. Great learning experience. Okay, so we got that in. We got it so that we could run. The next thing was, as I said before, 10% of the beam interacts in these targets. So here's a picture of our targets. We had this liquid deuterium. Off the screen to the left, we had liquid hydrogen. We also had some disks of solid targets. They were located on a table up here, and we moved them in and out of the beam in that 55 seconds between beam periods. And so the question was then, two of the things we had in here was a place where we had no target and a place where we had one of these flasks of hydrogen or deuterium, but it was pumped and empty. So the next question was 90% of your beam is interacting in this magnet. I said that, it doesn't let anything through except muons. But of course, there are muons produced in this, and there are muons produced between the targets and the dump from pions that decay. And so can we tell the difference between muons produced in this magnet and muons produced in our target that was just a few meters away? Remember that our tracking was clear up here, and it's a long projection back, and the muons are traveling a curved path through the magnet because they're charged, and they're losing energy in their multiple scattering. So to know you can do this experiment, you have to demonstrate that when there is a target in the beam, you see events, and when there is not, you don't. So this is I haven't taken the luminosity out, so there's no real information on physics in here. But when we have the hydrogen target in place, we see events. When we slide to the empty target, we don't see events. When we go back to the deuterium target, we see events. When we have no target, we don't see events. So that, and so on and so forth for the iron, carbon, and tungsten targets. So that basically tells us We saw the J psi before. We can tell the dump events from the target events, so we're ready to go. I skip now to this, which is actually after much work perfecting our tracking algorithms. This is our data spectrum that an invariant mass that we measured. On the low side here, the physics dictates that this keeps going up, but our detector acceptance is such that it cuts off. So those two are happening here. And what you see in the green is a Monte Carlo of our J psi in our experiment. In the blue is a Monte Carlo of our psi prime. In the red are the data we actually collected. And if you add everything together, you see that it adds nicely to what we actually saw. To make sure that there were no J psis or psi primes coming into our data, we put a mass cut at 4.5 GeV. As I look at this now, considered, can you still hear me? I just got a note on my computer that it.
Yes, we can. Paul, can you hear us? So now we don't, yeah, Paul? Now we cannot hear you.
Okay, now can you hear me?
Now we can hear you, yes.
Okay. Yes, my computer just did something to me. I apologize. I don't know what it did. So we considered this region above 4.5 GeV as our good Drell-Yan region. As you see, there's still some, in this plot, on a log scale, you can see that measurements from the empty target do leak into here. And there's a mixed random background that comes from two uncorrelated muons. So you could have a pi plus and a pi minus from the same 60,000 protons interacting in the target that then decay, and those muons make it through your experiment. And that's sort of represented by this green curve. And so we account for all of that. This is our Drell-Yan data. Then measuring, oh, I thought I was going somewhere else in this talk. Okay. So then what we want is the cross-section ratio of d bar over u bar, which is the cross-section ratio of liquid hydrogen to liquid deuterium. As I showed you before, there were massive differences in rate in the detector from one moment to another. And so the question was, does that rate actually have an influence in our ability to record this? So to first order, even though the hydrogen and deuterium targets had different interaction lengths, they had the same physical length, all the beam interacts up front there. And so to first order, all the beam interacts before the spectrometer, so there's not much of a rate dependence. To second order, though, as I said, there are different interaction lengths, so there are different amounts of beam that interact in the target and the dump, and that's separated over a meter or so. And so one has to look at, is there a residual rate dependence? So the easiest way to do that is to plot the ratio of hydrogen over deuterium, binned in units of the number of protons hitting the target during that particular 19 nanosecond window. So on the right here is a picture of that cross-section ratio, hydrogen to twice deuterium, as a function of the intensity of the beam that was hitting the target. And you see that there is, in fact, a residual rate dependence that we have to worry about. The final answer that we want looks like it depends on the number of protons hitting the target. And we all know that the physics, in fact, does not depend on the number of protons hitting the target. Well, so there are a couple ways you can deal with this. One way is to simply say, okay, I just want to look at pristine events. I'm putting a cut here at 10,000 protons hitting the target. I look here, and that tells me what the ratio is. You can do that. You lose all the statistical power from any of the data out here, which is the majority of your data. You could try to say, okay, there are a lot of effects going into this. So one, I know that when the chambers are full of hits, it's hard to track. So I lose tracks, and that'll cause an inefficiency. That could be different for hydrogen and deuterium because they're different densities. Another source could be that when there are lots of hits, the voltages in the photomultipliers might sag. And you can come up with many, many multiple effects. And so an option would be to model each of these effects, use Monte Carlo to verify them, and compare it with our data, and then use those models to take the effects out. The problem is there are lots of different things you have to model. So what we, so here, just to show you the distribution of intensity in our experiment, a lot of it was at low intensity. So this is normalized by beam bucket. So these there were a large number of these, but they had very few protons. But there were a significant number out here that had lots of protons at one particular time. So that was not good. So the way we chose to do this is to say what we're really interested in is what this ratio of hydrogen to deuterium is when there is only one proton coming down the beam. So basically zero intensity. So we adopted a method where we extrapolate using all the data. We do a fit and we extrapolate down to zero intensity. And so here are 6 of our bins in X of the target as a function of intensity, the cross-section ratio. The fit form we chose to use is given here. The yield on deuterium to twice the yield on hydrogen is equal to the intercept, that's the zero intensity value, plus something proportional to the intensity, plus something proportional to the intensity squared, where since the intensity didn't really care what value of X, there's no correlation between the X and the intensity, this A and B, these A and B parameters were the same for the simultaneous fits of all the bins. So then the only thing that varied bin-wise was the intercept. We tried many, many different forms. Of course, if you add parameters in, if you add X2 dependence or X beam or X target dependence, you get better and better chi-squareds, but the actual information content is also diluted. You can fit anything with enough parameters. And so after experimenting with many forms, this is the form we ended up with based on some information criteria that can be carried in the number of parameters. So if you do that, this is where those intercepts ended up, and this is the SEAQUEST cross-section ratio of twice hydrogen to of deuterium to twice hydrogen. And the first obvious thing that stands out is that the cross-section ratio is relatively flat and always positive, compared with the 866 data that came up to the cross-section ratio we measured, but then went back down and went below 1. So here I just plotted the first 3 points of the SEAQUEST cross-section, and you see in a region where they overlap with good statistics, they sort of agree. But that begs the question, should they agree? And so on the next plot here is a plot of CTEC 18 NLO calculated at the kinematics of NUSI in lavender and the kinematics of SEAQUEST in red. And what you see is they should come close to agreeing, like we saw, but they shouldn't actually agree because there are, in addition to X of the target here, other hidden variables that we simply integrated over. The X of the beam acceptance was not quite the same for the 2 experiments. The center of mass energy was a little bit different. So you expect close but not exact results, and that's actually what we saw. If you add the points out to higher X, I show here, The trend clearly does, however, disagree with what E866 NuSi saw, where the ratio goes below 1 and deuterium has a higher hydrogen has a higher cross section. We see out here with good statistics that that's not what is happening. Okay, so we would like to extract what we're interested in, d bar over u bar, from our data. Now, I said earlier, I gave this formula up in the upper right. Of course, I also said I was making lots of approximations. The correct way, I should say, to extract d bar over u bar from this data is to include it in a global fit with all the other world's data, because all of the parton distributions have correlations in them, and so you have to take that into account. We're working with the various groups to have that done. They're very interested in our data. Thank you, CTEC. And so that's the proper way. But we're interested in also, our curiosity is, what does our data just tell us? So we developed an iterative method to just simply extract d bar over u bar from our data, assuming that the global fits are omnipotent except for their knowledge of d bar over u bar. And so what we did is we computed the next leading, we integrated over the acceptance of a bin, computing the next leading order cross section of deuterium divided by twice that of hydrogen with some assumed d bar over u bar. We would then compare that with what we measured and iterate d bar over u bar and do this calculation again. And so you repeat this calculation until it converges. It converges actually fairly quickly if you make a judicial selection of your starting d bar over u bar. And from that, you can get what we measure for d bar over u bar in our experiment. And again, you see that d bar over u bar is greater than 1 for the entire range. Compared with the NuSi results, where again, in the region we overlap, there's reasonable agreement. You might argue this one point is a little low. I'll let you argue that. But as we go into the higher X region, there's a clear trend where SEAQUEST stays flat, and the acceptance of NuSi was tailing off. So we're at the very edge of the acceptance here rather than the center for SEAQUEST. And you see a clear difference between the two. The parton distributions I showed you before for the cross-section ratio, this is simply d bar over u bar at the kinematics of the two experiments from the PDFs. Now, this isn't really a fair plot because this fit that CTEC did includes this Drell-Yan data as one of the elements that it fit to. So in fact, this data would serve to pull these curves down, which it has done. Our data would have a pull upward, and that hasn't been included. Okay, so as I said earlier, there are also non-hadronic or non-perturbative degrees of freedom, and there are some models of the proton that have non-perturbative degrees of freedom. So I'm going to show two of them here. These two are chosen partially because they agree with our data, but they're also sort of representative in the way to model it. So the first one here is Broly and Sofer, and they, this is actually a combination of a fit and a model. So they fit to some of the deep inelastic scattering data, and within the context of their model that uses spin statistics to correlate things. And they get what I would say is quite good agreement with our data. When I talked to Broly over email the other day, he said he has some work to do to figure out why they missed our data. Two different interpretations. Another model, which doesn't include a fit to any data, well, it is Alberg and Miller, that use the PION model that I showed before in a little more complex or true way. And again, that without the input of DIS data actually does a very good job of describing what is happening here. It rises from a symmetric C to some sort of asymmetry, and then it levels off. Again, albeit slightly above our data, it has the right trends. Okay, so that is the SEAQUEST d bar over u bar data. I have a few minutes left, and I want to give you a very few minutes. I see that I want to give you a quick flavor for what we're doing next. So I said earlier we had iron, carbon, and tungsten targets as well. So we're using those to look at the EMC effect. And the EMC effect says that as you go to higher X, it appears that nuclei have fewer quarks in them, or the quark distributions are significantly different than that of deuterium. So on the left was measured with deep inelastic scattering. On the right is some data measured with Drell-Yan from 1990. And what you see is, rather than a consistent trend, here you see it's approximately level. Some go up, some go down a little bit, but within 1 sigma, it's level. I should point out, however, that many of the models at the time that described the EMC effect were PION excess models, and those predicted, in fact, that this ratio, the EMC effect, should be the opposite, and by the time you get out to X of 0.3, it should be much, much larger than what we actually saw, or than what was actually seen by E772. Okay, so I don't have much time. Here's some newer models. They do a little bit better agreeing with the 772 data, but they take advantage of the fact that there are large uncertainties. This is our preliminary data that has been shown before for the ratios of carbon to deuterium, iron to deuterium, and tungsten to deuterium. And here it is compared to the E772 data that I showed you earlier, with the important caveat that partonic energy loss might be important and might shift these distributions. And that's one of the things we're studying now to see how that affects this. Finally, in the near future, SEAQUEST is changing to SpinQuest, and we're exploring the C of the proton. We're all familiar with the proton spin problem. How do the quarks and gluons and orbital angular momentum add up to a spin 1/2 particle? So we've been able to measure the spin carried by the quarks and the strange quarks. Rick has given us an idea for a spin carried by the glue. We're now looking at what happens when all of these things are orbiting within the proton. There's some orbital angular momentum. I'll just skip over this quickly, but to say you can get a feel for what that is by measuring the Sivers function. It's been measured in semi-inclusive deep inelastic scattering for primarily sensitive to quarks. We want it, and then included in global fits. We want to measure it for anti-quarks, just like we did for the D bar U bar ratio. We're putting in a polarized hydrogen and a polarized deuterium target in our experiment. This is now, I see I left SpinQuest here. It's actually, I left SEAQUEST, it's actually SpinQuest now, putting in a polarized target that should be installed sometime late spring, early summer. We may be able to take commissioning beam on it this spring. We certainly will be able to in the fall. And so the uncertainties on hydrogen and deuterium that we expect to be able to measure are shown here on the right, compared with two different models that fit the semi-inclusive deep inelastic scattering data to see what we can expect to see. So one last fun thing that this paper has done for me is it's taught me how the press works. So we have received, once we published in Nature, we have received a lot of coverage in a variety of sources. My son was the one who pointed out Reddit to me. For one day, we were the top trending article or post in physics in Reddit. The Mars lander landed that week and we just dropped off site. But it was fun to be covered by all these places. And one added benefit is they do nice graphics. So I asked Argonne's graphics people if they could give me some time to do some graphics for this, and they basically had no time. But the media did have time to do it, and they came up with great graphics, except you can't look too closely at them. So on the right here is a model of the proton from Quantum Magazine. And if you look closely at it, it has almost as many top anti-top pairs in it as it has up or down pairs. So great graphics, not quite correct. Okay, so what do I want you to take away from this? Since I'm basically out of time, I want you to take away first, Feynman makes everything look easy. He just says, I think it's this way, and it turns out he's right. The second thing is Drell-Yan provides access to anti-quark distributions, and we have measured these anti-quark distributions, and they show that there is a d bar over u bar asymmetry, and this asymmetry persists out to large X into regimes where one of those anti-quarks is carrying 40% of the momentum of the proton. We are also studying nuclear dependencies, and in the near future, we'll be having polarized targets and studying spin dependencies of the anti-quarks. So that's all I wanted to say. I'm sorry I went over a little bit, but I'm happy to stay on and answer your questions.
Right, we have a couple of questions in Q&A. Amanda, are you able to unmute?
Yeah, can you hear me?
Yes.
Yes.
Right, well, I typed them in, and the first one was just that if you go back to a slide where you were comparing the results on the EMC effect for deep inelastic scattering and Drell-Yan. Sorry, I can't recall what the number of the slide was. Yes, yeah, sorry, just go.
This one.
Yes, that one. What struck me was that your Drell-Yan finishes at X of around 0.3.
Yes.
And if I go over to the deep inelastic scattering one, at 0.3, it's also still sort of even.
Yes.
It only starts to drop after that. So
yes,
I
you're quite right there.
There's really a contradiction.
You're quite right there. The contradiction comes in when you look at the models that are used to explain the EMC effect. And those models predict a large excess, basically an opposite of the EMC effect, to appear in Drell-Yan, and they predict it to appear at a low X. So if you look over at the right, this dashed line was a PION excess model, but it was typical of most of the models at the time. And it predicts, to account for the data on the left, an effect on the plots on the right that should be easily seen.
Right,
so
right.
At that X range. So you're right. We don't go into we do, but E772 did not go into the range where you would see, if it's the same effect, they didn't go into the range where you would see the same effect.
Okay. And the second question I had was just a bit provocative in that, do you have any comment on what might have gone wrong at the high X with the E866, which is suggesting D bar is less than U bar?
Yeah, that is okay, so that's a question I have spent a whole lot of time working on. I was the postdoc who did the analysis on the E866 experiment. So that is also my work. And we have been able to find no reason for either data set to be incorrect. I should say, however, that the E866 data was on the very edge of the acceptance. And so there could be something having to do with the edge of the acceptance. Because of that, it naturally has lower statistics. The E866 experiment was actually designed to look at low X, simply because that's where they thought that the difference in D bar over U bar would be most prevalent. So it's unfortunate, but we have no explanation. All I can say is SEAQUEST was designed to look in this region.
Yeah,
so-
it's just, it's sort of, it's amusing just because this shape coming down again has influenced a lot of the PDF fits for a long time. So
You call it amusing. I sort of spent a lot of time not being amused by it.
you've got to laugh, you know.
Yeah.
Thank you.
Mm-hmm.
Robert, does that answer your question, or you had additional question?
I'll perhaps put a slightly different twist on it, if that's okay, because it was a very similar question. However, in global fits, when we have a new set of data that is basically a measurement of the same sort of thing, quite often we throw the old one away, but only if it completely supersedes it. In this case, it's clear that it doesn't supersede it. There is a definite tension between the two. And normally we would simply fit both data sets, which would probably get us something here where V bar over U bar tends to something like 1 at high X, rather than remaining greater than 1 or going negative. So can you give us any reason why we should not now simply include both data sets?
So, you know, as I said, I worked on both experiments, and I haven't been able to find anything wrong with the 866 experiment, and I've tried. Clearly at low X, below 0.15 or 0.2, you only have the 866 data, and I think you should use it. Above 0.25, it was on the edge of the acceptance. And we're worried about that, but we haven't found a reason that in and of itself is a problem. So that does create some tension. And as I said, I did not find it amusing. I've looked at this for a long time.
Well, it is certainly the case that in some places we see different data sets pulling in different directions. And sometimes they are data sets that measure essentially the same sort of thing.
Mm-hmm.
And the best fit is currently a compromise between them rather than one or the other. So you're suggesting that may be true here.
It may be true. Right now, I tend to believe, okay. Now you're going into my personal speculation on which is correct, because I can't give you a physics reason other than the fact that that last point in 866 was really out on the edge of the acceptance. And so my belief is that you know the center of the acceptance better than you know the edge of the acceptance. And so where we centered it in SEAQUEST, we actually, and this is the center of our acceptance, we have data going out to higher X that we hope to add to this eventually, but we just wanted to get the center of our acceptance out there. So it's a question of how much you trust the edge to the center. And so my personal feeling is I like the 906 SEAQUEST data because I know we're centered in the acceptance. That said, as I said, I can't find anything wrong with the other data.
I think perhaps just one comment there is that it's clear that the best fit to the 906 data is going to be a pretty poor fit to the 866 data over a reasonably wide region. It's not just that one point.
Yes, there's nothing I can say. I've studied these and I can't find any reason on either one.
Okay, thanks.
Jose?
Yeah, hi, Paul. Very nice talk.
Thank you.
I have a question regarding the systematic errors.
Yes.
How much of this error is actually correlated between the points, and how much is in common shifting the data up and down for all the points together?
So it is basically all shifting the points up and down for all the points together.
Okay.
So so there's two major sources of systematics here. The first one comes from the relative luminosity measurement, which we quote at 2%. The second one comes from this correlated fit that we did to get rid of the intensity issues. So since we correlated the intensity dependence between all of the bins, that has a big effect and correlates. And so that's the biggest systematic uncertainty, and it correlates them between all the bins.
Okay, very good. Thank you.
Mm-hmm.
I think next is Hugh Montgomery.
Hi, Paul. That's a very nice talk. In my memory, Feynman actually also predicted that U bar be greater than, D bar be greater than U bar based on Pauli exclusion thinking.
Yes.
Is that correct?
It is correct that he predicted that. It was a very, very simple argument, though. And other authors who I would have to look up to give you a reference to, I can't do it off the top of my head, did more careful calculations of that, and they found that that, in fact, didn't contribute significantly to this. While I can't reproduce the calculations, one way to think about it is once you have pair produced half a dozen pairs, the counting certificate, the difference between 1 and 2 and the spin statistics doesn't really matter that much. The other thing you have to remember is that in addition to flavor, there's the color component to the Pauli exclusion principle. And so while there is already a U quark, it's got one color, there is still room to pop in 2 more U quarks of the other 2 colors, UU bar pairs that carry the other color anti-color. And so that, immediately washes out this 2-to-1 ratio.
Okay, thank you.
Mm-hmm. So those are just my ways to think of it. If you press me, I can go back and look through references and find a paper that actually went through the calculations.
No, that's fine.
Okay, so we have many questions, so maybe we'll just go in slightly different order. John Wei Chu, did you want to ask the question yourself?
Yes, Paul, thanks for that very nice talk. Then I have a quick question. In your approach to extract the D bar over U bar, you did this iterative method by calculating next leading order prediction, then by choosing a D bar over U bar, then compare with data, iterate, eventually get a D bar over U bar.
Mm-hmm.
So when you do this next leading order calculation, did you take into account any nuclear effect for deuterium?
No, we didn't. We did put in our systematic uncertainty, we assigned a small value for that, I believe. But that's a good question. One of the reasons we put the heavy targets in was to see if there was something we could extrapolate back to the deuteron to just put a limit on it. But no, we didn't do that.
Okay, thanks.
Yep.
Thank you. Uta?
Yeah, hi. Yeah, very, very interesting. By the way, just as a follow-up question and a little bit different than I put here, did you measure the cross-section that you really could compare?
Yes, so we measured the cross-section. That paper is still forthcoming. As you know, many of the systematics just cancel out when you measure ratios. So we got the ratio out, but we did measure the cross-sections.
Yeah.
One of the uncertainties that comes in the absolute cross-sections is the absolute beam normalization, which cancels out in the ratios. And so that, is going to be a significant, well, not significant.
Yeah, thank you, because this is extremely interesting for the PDF fits, if you then have really sigma D and sigma P with correlations. Yeah. So, and this is pretty cool. But actually, my question was more to SpinQuest, to be honest. Are you putting these polarized targets sequential in time or parallel?
So what we have is a system much like what we did in SEAQUEST, where we have a table and we can switch them between spills. So in SpinQuest, we can't switch them that often, but we're going to, switch them on, I forget what basis, but, a day of one data, a day of another data type of thing.
Because my worry is time dependencies.
Yes.
If you are measuring asymmetries, the time dependencies are a headache. Because I was with Hermes and fighting with time dependencies.
Yes, and that that's why we change targets in this experiment every minute. But we do want to change them as frequently as we can in SpinQuest.
Oh, yeah, this would be good luck.
Thank you.
Paul, the other interesting remark you made is that there will be very important measurements of these cross-sections on nuclear targets. And again, there is a puzzle related to the behavior of quark PDFs in various nuclear targets. When do you expect this data to be published roughly?
We were hoping to have a preliminary presentation at the APS meeting, and we just didn't make it. We didn't, so we're close. Publication takes a little bit longer, but at least something, we were shooting for the APS meeting, didn't make it.
Okay. Okay, well, we are out of time, and
I actually had a question.
Yeah, Tim, yes.
Yeah, I don't know why it was missed. So yeah, Paul, thanks for the really excellent talk. My question is related to a couple that were asked. It's clear from your talk that this proton beam intensity variation uncertainty is really an important systematic. I was wondering if you could elaborate on what you said. So, I mean, for E906, do the zero intensity extrapolation. I understand that that results in just a fully correlated uncertainty. You mentioned for E866 that some sort of Monte Carlo procedure was used. I was wondering, could you comment on any difference between the two approaches and whether that might induce, for instance, some sort of X target independence for E866 compared to E906?
That's an interesting thought. I should go back to Rusty Towell's thesis and look at it. My memory, E866, while it had a rate dependence, it was nowhere near as strong as this rate dependence. So they took data. First, their beam was spread over 20 seconds rather than 4 seconds, and they had an order of magnitude less protons coming in. So while they had a rate dependence, it wasn't on this order. We looked at it. We did model it in Monte Carlo as simply by adding random extra hits.
Right.
So you pose a good question that I have to go back to Rusty's thesis and look at.
Yeah, it'd be interesting to see.
Yeah.
Right. Okay. Well, thank you, Paul.
Mm-hmm.
Okay. Well, just to be sure that we did not miss anyone, are there any perhaps last-minute questions to ask Paul? Okay, if not, Paul, thank you so much for this excellent presentation. And indeed, we look forward to the analysis of this important data that hopefully will help us to resolve this long-standing question about the anti-quarks at large momentum fractions. And with this, I think we are ready to finish our seminar. I would like to also thank all the participants and well, thank you especially for the very interesting questions after the talk. And I wish you to have a good day and hopefully we'll meet again at the next CTEC webinar in the near future.
Thank you.
Thank you.